Okay, this will be fun. I'm actually really excited about this because today we're going to talk about two things. And when I reviewed the exams, you know, I looked at the question banks. I thought, look, we're beyond data analysis, so why should we even use R? And I'll give you two good reasons to continue with R. First of all, this is just another way to look at a different angle to look at the material. So if you want to look at the material the way you have been before, attend Ethan's review section, attend other review sections. This is a useful tool because whenever you're acquiring information, evidence shows repetition helps, but also multi-methods, different sensory inputs actually, different sensory inputs actually really helps. An ancient Greek technique of learning is actually the method of loci. The ancient Greeks would remember these long passages because they were always, I think this is a Greek word, peripatetic. It used to be a philosophical thing to hold hands and walk in a little quad, and you would remember things because as you pass, say, a certain column, oh, I'm associating this object with that. And there's famous cases of synesthesia, which is the combination of tastes and sounds and other senses. It's deeply encoded in your emotions and in your brains. Related to data science, there is a new movement to connect data and visualization to music, which I think is really fascinating as a musician. So long story short, one useful way to think of this is just another strain or avenue to understand and interpret the logic and reasoning of problem solving, and then the interpretation of the results as they go through real time. And we can even pick some examples. For instance, I have some in mind that aren't the same data sets that we've been using ad infinitum. We can actually deal with new stuff. And if you like programming and that kind of stuff, then this is also very useful. I'm actually going to go to my global options. I'm going to make this my console, my scripting console. The code right here, appearance. I'm going to make it, there's a default here. I think it's Cobalt. No. Well, that looks about, oh, I'm not sure which one it is, but it's one of those. I think it'll look a little bit better. Okay. Thank you. Got to do a screen share. Let's share the screen. Okay, now you see it. So here you see the black screen. What I did is I just selected an option, and I went to global options. I went here, and as you saw before, I think I had something like this. You know, if you want to look really cyberpunk or 1980s, you can don your yellow sunglasses and your yellow glasses and hack your way through. But I'm going to stick with this white. I think it'll be more familiar to us because this is how you're going to see R in most of its glory. So, as you'll see, I'm doing this. I decided to gotta save this. We'll save this to the desktop, and we'll just call this R final, and it'll automatically remember where it is. And then we can always do this sort of nesting function, get. So get working directory, and then we're going to nest our function. We'll do set working directory. What do I do? Set get. Oh, I need a WD. It's funny when you see some of the pros. I'm going to do it this way. I actually like to define these separately. I like to find my working directory and see it printed out. This just grabs it as a string. It's technically a vector. You can actually know that to be the case. You can type this as class function. Tells us what these objects are. That's a character. Okay. Okay, so that's a type of, technically there are 4 or 5 different kinds of numbers. There's a character, there's a logical, which we're not really going to deal with. And then there's character, there's integer, which is a floating point number. It takes up more space. And then there's the integer, which is just a subtype of the number, which is You know, that's what you can count. Add to infinity, positive and negative. I'm going to remove the working directory because it looks like it's not exactly where we want to be. Well, we'll do that again. Okay, because I just want to cut and paste this. Oh, it doesn't. It does. This doesn't matter. I don't really care where we are right now. You know why? Because we're just going to do a little bit of math here, and this will give us, I think, the best insight into the way R can work. This, in terms of, if you could just give me an indication. I know we could technically vote. Can you tell me if you have taken a gander at the, when you have the answers correct or incorrect, you'll see some script from the problem set 9. Did you have a chance to take a look at that? Quite a few of those had pretty elaborate script on rounding and all that kind of jazz. Did you have a chance to take a look at that, I wonder? If not, can you say, can I get a negative too? You didn't look at it? No indictment, nothing, no worries. I just want to get a feel for that. Okay, maybe you can't hear me. Okay, that's fine. So I want to close this. Where the heck is this? Okay, so here we have 3 RStudio open files open. Okay. Okay, so look, this is how I think about math in R. And I talk about this because this is just how you use it as a calculator. And I realize you cannot see that very well. We're going to actually change this back to an appearance, a much darker appearance. We'll do, because I think you're going to see that a little bit better. Okay. All right. So this is what I want to say. I kind of want to say fancy calculator, but that's a little diminutive, I think. There are 4 things we can say that R can do when you do math, and these are going to be relevant as you're opening files, and then you can open this. Basic arithmetic operators. This is most of what you'll need for class. Math functions, which we do a little bit of, especially when we solve some problems, and I'll give those to you. You can have these in a technical calculator, TI-85 or whatever, Texas Instruments. If you go on the internet and watch, I think, a Vox video, it describes how Texas Instruments, why do we still have calculators in today's day and age? Well, there's a video out there on the internet that explains this. But you can do it right here in your own home. But you can't document that as syntax. You can also do elements of vectors that define groups or sets. So that's sort of, just think of that as when I think of a vector in R, I'm not sure if there's another computer science term, but think of just a concatenation of numbers, for instance, and then you're going to mathematically apply to each of those. Vector operations operate on the whole list, so it would be like a total or cumulative sum. And then there are matrix operations, such as a data frame. A lot of the people with a lot of programming experience are basically, I've seen them do this, the vector operations, which is, to me, it's quite impressive, because it's nothing we really teach. And I think Mosaic is it's an interesting sort of, it's its own world, really. It's a world within a world, because I think it's simpler. The syntax is simpler. But the point is, you can define a matrix, which is a box, really. I kind of think of it as a square that's evenly defined, that has an index of rows and columns. This is what we've loaded up with data sets. A vector is just one of those rows or columns, right? Elements are just each of the little cells if we had an Excel sheet. So let's start with these math functions. All right, we're going to go through this pretty quickly, because then we're going to go to interpretation of output. Right, so I think this is pretty simple. And as we talk about it, I'm also going to talk a little bit about style. if you notice something, I have a little bit of a line here. And you'll see I have this little thing here. I put some of these little dashes and a little comment here. I like to, it's a way of sort of organizing everything. Typically I'll have, in LaTeX you'll call it a preamble, but this is sort of like where you, set, this is where you sort of really load your packages, right? Load, Mosaic. I like to do this. And so a lot of this is informed by the Google style guide. So Google has its own definition. I said load because that's not the right function. You have to do library, install pack, and you should always do install packages, and type that there, right? I don't know if you notice this, but within RStudio, you can just type quotes once, and then you can just type in your text, right? So Mosaic. All right. But I'm going to comment that out. I highlight it. I press Control-Shift-C, and then it's commented out. And that's a nice thing with RStudio too. If you highlight all of this, you can do Control-Shift-C and comment it. Oh, wait, I can't uncomment this. Do you know why? Because you have to select only those comments. And then if I type Control-Alt-C on a PC, I think it's Command-Shift-C. Sorry, Control-Shift-C. I think if you type Command-Shift-C, you'll be able to uncomment those comments as long as you highlight those. This is really good when you're working, especially if you're, have a lot of math problems that you're going to work through, and you want to, you don't want to deal with it anymore. You can turn it on and off. Okay. Okay. Notice you can also do this little comment afterwards. So what do we got? We got addition. We're aware of the plus sign here. So this isn't always the case. The caveat here. This is sometimes a little confusing, right? But we got that. Okay, and we define that. If you notice in my environment, I always like to look at the environment personally. There are also things called hidden objects. They're indexed with a little dot here. The way I set up my environment, you can actually see the last object I defined. That's also another criticism of R, but you won't have that, probably. No worries. I asked the smartest people I've known who are close to the developers of R. They don't know how I got this, but you should look like a blank space. You can subtract. Why does it say error with library? There you go. Okay, but here's the point with this, right? When you do math, it's always going to evaluate the expression left to right. Okay, that might sound trivial, but it kind of makes a little sense, right? But just keep that in mind, because there are a lot of things you can do in R where I can define, say, foo, and then I go like this, and I can do, well, that reads left to right. But, oh, this is even kind of tricky. You can actually assign the operator this way. Oh, it doesn't, I guess. Not for me. Well, whatever. What I was trying to show is that evaluating the script left to right isn't always going to happen, especially when you define functions. I wasn't able to give you a quick illustration of that there, but just this is key. And of course, it doesn't matter if you do addition or multiplication. These are the only operators you can use for these, by the way, just FYI. You can do things different ways with other operators. There's the division sign, right? Okay. If you want to raise something to the power of the 4, you put this little caret there. Now, look what I'm doing here. I'm putting spaces between all of the operators here. That's standard syntax. You're going to have an easier life. If you're a purist, maybe you'll do that. I kind of don't like that. I kind of like to, maybe it's just me. I like to put my power, raise a value to a power by doing the caret and keeping those together. And it'll print on the screen, if you notice this. And the other thing to notice with R is, look at this little index here. What is it doing here? Well, it's actually telling us that we actually have a vector of 1. So you can actually define these as vectors. It's already thinking in terms of vectors. Because so this is where you type. This is the command, and this is what it's really telling us. If you sometimes when you scroll over items in RStudio, it'll tell you what it is. But anyway, those are important. Okay. Now, the other thing to think about is, were there any questions? Don, did you have a question about referencing something? I just meant subtraction, the order of subtraction matters. That's nothing really more interesting than that. Okay. Did you have another question, or? Oh. About maybe putting spaces here, about, what was there any particular issue of concern? Oh, okay, good. I'll bring up problem set 9, and we'll start with an example of that. So if you go back to the assignments and then look at the grades and look at your assignments, you should see when you review the submitted assignments, even when you get an answer right for some of the answers, you should be able to see code or script written. And because I wrote out code that would give you an answer for every single numeric question. If you're not seeing that, please do tell me, because that needs to be there. Sounds like you're not, though. So that's all I was saying, and I'll give you an example of that. Let's see. You didn't see that. So I want to clarify and see if I can see if I have that. Okay, well, if anyone else, can anyone else check maybe? Okay, or not, that's okay too. But you should be able to see that, and that's a resource for you. Hold on, I'm actually gonna go to, I want to show this, I actually want to show this to you because this is actually quite important. If you haven't seen this, it's actually extremely important to look at. Okay. If you look at, okay. I'll bring this up. I'll bring this up to the script, and I'll show. We'll actually use this first, because there should be a lot of syntax here. All right. So one question. We'll start with this. This is actually a really good example from the problem set 9. We had in that exam this kind of question. And we'll just use some operators here. Oh, before we do that, I want to give you just an example of the functions that you're going to use here. Right? So you have that power function. The next one you're going to use is the square root. Right? So these are functions. What is a function? Well, it's like everything else. It's not these little things called operators. This is whatever you put in here. So the square root of 4 is 2. This is what you're going to have to do. I got to put a Q there. And by the way, you can just highlight the last of that syntax to Control Enter. You don't, and not even highlight it, if you just put the cursor there. If you have multi-lines of code, you can actually put the cursor to the top of that line of code, and it will evaluate all of that. So that's, I think, super duper handy.
In my
other kinds of functions you're going to use, I don't think you're going to use that much, but let's talk about this. Sometimes you may be interested in this. This is an absolute value function. So this will return the absolute value of anything that you have inside parentheses. It gives you a 4. What's probably going to be a little bit more common is a log function. Now, the log function is generic in the sense that you can do a log with any kind of base. So the first part of the argument is the number, and then you do a comma, base equals, probably base 10 is what's quite common. Now, if there's nothing here, if it's just the log 4, that's the natural log, right? So and then here's a base log of 10, base log 10. Square root is going to be something here. Other than that, we're really not going to use the rest of these functions, I don't think, unless you have any functions. Oh, cool. You just evaluate, say, if I want to evaluate this line of code, I'll hit enter. See, when I hit carriage return, it'll actually enter into the next line. I will create another line. Oh, it's Jason. Sorry. Do you have a PC? Is it operating system 10? I'm typing right in the console. Sorry, the scripting window. If you are in the console, this is interactive, right? Console is interactive, so whatever you type, I don't like to do that because I will forget what I just did. All right? That will let you do whatever you want. You can probably do square root of 4,000, and you just stick it right in the middle. You can put it right at the beginning and hit enter. It'll evaluate it. Yeah, so the console is interactive. I discourage that. I always encourage you to put your stuff here because you're going to reuse it. If you do it once, never do it again. I don't want to talk any more about operators. Thank you, Adam, for asking. So, yeah. Okay. Any other questions about mathematical functions? I don't think we need any more than that. I know a lot of this is basic algebra, right? Okay, we know all this kind of stuff. I'm going to talk a little bit about writing numbers, and this is kind of interesting. Not everyone in the class is familiar with scientific notation, but we see it all the time in the output. In fact, see, I just printed that number. You can type this. If you type print within a number, you'll print it. That's probably the proper way, but anytime you type anything here and you press Control Enter in the console, well, I won't do it there because that's a string. You have to put that in quotes. It'll print out the string. But numbers, yeah, it'll print it out. Well, okay, you can do that. But why do we not want to do this? Well, because we're going to make a lot of errors. And when you see very small p-values or very large values, you're going to make mistakes, which is why you see the kind of output that you do in R. So another way to write this number, for example, is through our math functions and operators, right? 10 to the 5th. So we're taking 10 and taking it to the 5th power, which is going to be 5 grand. I think, no, whatever. And then we're going to multiply, I forget it. This is scientific notation, though. I see you get at some point you get so used to saying it. That's intuitive. And that's the same number. This is me being sort of embarrassingly naive here. Oh, yeah. So, right, so it's pulling those, it's adding those zeros here. And this takes me to this little thing, which is a little idiosyncratic. But the point is, R evaluates this in the same way as it does this. That's kind of intuitive, but the neat thing you can do is that you can type this number using this E, this little exponentiation value, I guess you could say. But it's not. It's scientific notation. So let's go up to our script here, right? Here we got, what is this? We got 144,000. That'd be a nice salary. Here we have it in scientific notation. And then here we have it in scientific notation a la R. And this is how you're going to see a lot of these p-values, for instance. It's a lowercase e and a 5. And let's print that. Wow, isn't that cool? So the point is, when you write numbers and do mathematical operations, you can do whatever R wants. Similarly, you can do this with this small value. So these are examples with large values. And these reduce error. I'm telling you this not as an academic exercise. It's because we do reduce error. That's exactly what we want to do. And I'm talking about not standard error. I'm talking about human error. We do lots of different things. This is just, it's called literate programming if you want to look at the R databases, right? So another common issue to see are these really minuscule p-values. You'll have something that's really significant statistically. So here it is, written in full glory. Wow, that's ugly. I can't even count that many zeros, only bifocals. Well, in scientific notation, just as a quick refresher, if you want to move that decimal place over to the right, you have a negative exponentiation. If you want to move that decimal place over to the left, you have a positive. I'm going to put a plus sign here because I think this is going to evaluate the same way. Yeah. So technically, there's sort of an implied positive there. We don't put that there because we kind of think of that as an operator, actually. But of course, the minus sign is both an operator and a sign of whether the position of the number on the number line. Okay, so we can do this with small numbers. Now, guess what? We can just do this. We can type 4.31. What does the rest of this look like? E minus 6 or 06? Well, let's just try E minus 6, see what prints there. It looks like you got to type 06 here. Oh, look at that. It will evaluate what I just have here. How do we get back to printing that as a well, that doesn't matter. I think there is a way to reprint this back, to expand this out. Just trying to remember how that was. It's not really that important in terms of output. It's more important in terms of understanding the fact that you can use these as inputs. Now, the other thing is now we're going to combine our fancy dancy numbers, our operators, and our functions. And I'm going to show you something that is useful. Oh, gosh, this is a pain. You're going to make a lot of mistakes here. Well, good news is you can actually type these very same things. And you get this exact same number. So good news. We're not going to deal too much with vector operators. I think it's just a little bit, I just want to see if there's something relevant here. I think it's important to deal with this class arguments. This isn't a numeric function, but this is a very useful function. Because what R stores, not only numbers or characters, it also stores classes. It tells us what kind of object it is. I talked about vectors. There's a thing called lists. I'm not exactly 100% sure what lists are. I believe a vector is a list that actually indexes the ordering of those values. In the same way, if we open load, I'm going to load a data set here. This is a famous one called, well, what? Oh, I'll just do empty cars. I see with some of these data sets, you can actually just type this, and it's printed here, but I'm going to do view empty cars. See if we can load that. Yeah. So the point here is, well, maybe this one doesn't have it because I'm not loading it as a local database, but see, I'll load it as a, I'm just going to do something a little funky here, but because it's a built-in data set. No. What I'm doing is I'm loading this as a local data frame. Well, whatever. It doesn't matter. The point is, when you see a data frame, you'll actually see the first row, and you'll actually see this as an option if you read in a CSV file. You'll actually see a load in And that first row is actually not even a variable, right? It's an index. That's what a vector does. I just press Control L. I like to have a clear console, just my personality. But let's go back to this thing called class. It isn't just what classy people have, right? Class tells us, gives us attributes of an object. It tells us what in the world we're dealing with. So if you're ever wondering, is this a number, this thing, or is it a bunch of letters? It'll tell us. 99% of the time, you're going to be dealing with numbers. And if it's the only other time would be, so it's numeric. The only other time would be, sometimes you might be dealing with integers. That you shouldn't encounter any problems substantively. Integers save space because a floating point number actually has a limit to it. And I'll give you the number of values a floating point number can actually have. Do the programmers know? I don't know. I didn't know this. I think I did, and then I forgot. I think it was like the first day in CS or something. But I like to put, by the way, I like to put my operations in parentheses just to define it. It's more cosmetic. I think it helps me to think about things clearly. I get a little anxious if I see even just like a ratio without parentheses there. That's just, again, that's me. Your programming style might be different. So this is a very large number, right? When I did the cards function, and I showed that if you just shuffle a deck of cards, you will have done something that no one on the planet has ever done. This is, I don't even know how large. This is larger than that. Well, this is actually as large as you can get. It's the largest computable number on most machines. Test it on yours. And I'm going to tell you this because there is a little weird thing that happens here. And this is just something to be aware of. There is a silly function called isInfinite. I say it's a little silly because, okay, this number is not infinite or finite. What we're going to do is infinite. You can actually do that, you know. And there are a lot of functions, by the way, that have this sort of dotted format. And you can just type IS. You'll see the window pop up. I didn't type anything else. And you can scroll through. Speaking of which, I'm sort of changing my thoughts on the way I personally define objects when if I want to define something like a data set. I'm actually now moving toward using underscores for this very reason. A lot of functions use dots. And it gets kind of confusing if you have a lot of functions that have dots and then you say load data sets that are also like, is Nate's data set? Well, then it gets confusing. Is integer is actually quite useful. But there are a lot of things, if you want to know what something is, this is useful. But this is kind of interesting. I just thought just a little thing. Well, is it infinite? Not really. Is it infinite if I do this? What do we think? This is infinite? How can this be? The machine is broken. Nothing is sacred. Well, there are some limits to the programming environment. No consequences. I can guarantee you that. Google survives. Businesses are run. I believe even cars and planes are built using R. Medical decisions are made every day using R. I know people who work in hospitals. Don't worry. But the point is that there's a bit of a limitation here. So you can do that test yourself. See if you can have more space. But typically that's because of what is called the floating point number. That's not really as relevant as this whole question about decimal places. How many should you round to? Well, the point with the thing to remember is that R evaluates to 16 decimal places. All right? Anything you do will evaluate to 16 decimal places. And I'm going to introduce to you a function that limits console output, but maintains the precision you want. So we've used a lot of the rounding function. There is this generic function called options. There's a lot you can do with options, actually. option setting. You can do usage. There are a lot of different things. I think you can do, if we look at this, we can actually do digits. Then this, and I'll read this verbatim because it's clear. Controls the number of digits to print when printing numeric values. It is a suggestion only. Valid values are 1 through 22. So I must have said 16 decimal places. With default 7. So see the note about print default about values greater than 15. Okay, so when you print an argument, it'll print it to 15. But the point is, we often don't want to see 7. So if you want to see fewer, and you don't want to muck around with the data, I don't know if your little calculator will do that, but R will let you do that, and that's just a nice way to live, I think, because then you can just do if we do let's see, head empty cars. This is just a silly data set of cars. You see, oh no, you see a couple data sets. I'm looking for something as a tally function. Looks like that first one I thought would be a variable. I'm gonna actually load at one of our familiar data sets actually, because it will, familiarity breeds contempt, but it's also what we know. It's better to deal with the devil you do know than the one you don't. I'm actually going to open the data set for problem set 9. Now, how does this deal with the final exam? We're talking about precision when you're writing numbers, and we're talking about when you're evaluating functions and deriving answers, and you actually want to round, but you don't want to actually alter the information. You don't want to destroy information. The options function setting to digits helps. But the crucial point is it's not going to muck up your equation. If you look at a lot of what we've done and a lot of what I've written, I use the round function, and we'll get to that. But rounding, there's something called midpoint rounding, and that's a big no. You shouldn't do that. I'm adamant about that. We're flexible about this because we haven't really taught you that, and it's really not a main point of the course. But you should really distinguish between two kinds of doing work. One is for illustration. So those are the lectures. So if you see a standard error that is then reevaluated and inserted to estimate a margin of error, but it's based on a rounded standard error, we have a problem, Houston, because we have now destroyed our information, and we can come up with a very different problem. And actually, to illustrate this point, well, I want to go back to the rounding, but before we do that, I want to actually load the problem 9 data set and just go through this and show the virtues of rounding without having to actually muck around with the data, keeping those data precise to 16 odd decimal places. So, we're talking about writing. So in this section, I'm trying to emphasize that when you can evaluate objects, you can know what they are, and R works within a certain range of precision. It goes up to an extremely large positive number, and then it can evaluate to enough decimal places that it doesn't really keep me up at night too much. A little bit. I'd like to see more decimal places. 16 doesn't seem to cut it, but it's enough for everything that we're going to do. And we can keep that precision by using this options function. So I'm going to go to my desktop. I'm going to go to the course, and we'll use problem set number 9, which was on contingency tables. We're going to load the Wall Street data set. Yep, we do want to load it. Okay, so here are the Wall Street data set, and we'll load this. Load Wall Street. Oh, it is already loaded. I'm sorry. So let's look at the names of the Wall Street data set, right? So let's just do a simple tally function, right? Notice I haven't changed anything. So this is what you see is what you get. Remember the tally function is a tilde, and then we have, we'll do gender, and it'll be social class. I don't think we've looked at that. Data equals Wall Street. Look what I'm doing here. I'm actually making the format in a different order. For these arguments, the order often doesn't really matter. Format proportion, and you're going to see what you normally see. I'm going to hit enter, enter, because I like that spaces, and now I'm going to hit control enter. Oh, do you know why? Because I didn't load my function, my library. Could not find function library because I misspelled library. See, this is what you call the propagation of error. There's this whole concept of paired programming, actually. I've worked in scientific social science laboratories where I'm the only person who's the coder. I don't like that. You should never be the smartest person in the room because you're going to make mistakes. Okay, we got that installed. Okay, this is what we see, right? I don't like this. So what we can do is we can do options. This is one of many options they have. Digits equals, I love how it does this. It's kind of like Python. Controls the number of digits to print when printing numeric values. It is a suggestion only. Okay, so it's up to 22. I don't know why I thought I guess I thought it was 16. So I believe this is not scientific notation. So got to think about when you're printing digits. First of all, when you print digits this way, here are a couple things. You got to reset it to the default of 7, and you got to remember the default to 7. If you don't, although, well, I think these zeros might not even count as digits, to be honest, because zeros really mean nothing in the probabilities in the sample space. But the point is, if you're going to set your number of digits, it's going to stay that way, and that can cause errors. That's why I'm a little worried about it. So you just got to remember it's going to hang around. I was going to say something else. Oh, yeah. It doesn't do scientific notation. That's an entirely different issue. It's kind of a brute force mechanism, right? So the default is 7. Just remember that. We'll put this to 2, I believe, because I don't think the 0 before the decimal is actually even considered. What am I doing here? I'm going to put this right down here. By the way, when I'm writing syntax, I almost always comment more than this. So we're going to have 2 digits here. And then now when we redo the tally function, well, that's interesting. I wonder why it does that. I actually haven't seen that before. Okay. I swear I have never seen that before. What would that mean? Well, I guess there's another reason not to do it, right? The other reason not to do the digits function, of course, as I said before, is you can do. Actually, let's do this. Let's print 3.44444. Oh, let's do 1, 2, 3, 4. 1, 2, 3, 4, 5. If you print that, now it'll print to 1 digit. Okay, so this is what I don't like about R sometimes. So see how I set the number of digits to 1? Well, yeah, I did. And it works there, but it doesn't work with these Mosaic packages, which seem to have their own, they have dependencies. They take some older source packages and then sort of rewrap them and scrunch them up into a new format. So that's a little disconcerting for that. And there we are. We're back to where we were supposed to see the number. So maybe you can use digits for that. From my experience, I actually have never seen the numbers vary. But I get a little wary with tally. And actually, I get wary because on the first page of the Student's Guide to R, they say there will be bugs in their code. And I've seen that, actually. The correlation function doesn't work for 2 variables in one of the data set. So that's a little worrisome. Rounding, however, after you just find out what the final result is, doesn't seem to have a problem. Still, it is something to do. Now, hold on for a second. Why wouldn't this work? Okay, yeah, it's still evaluating 3. So for some reason, it's incorrectly evaluating 2. But if we evaluate to 4 digits, it's evaluate 3 is a 4. So somehow it's somehow adding a digit there. That's strange. Okay, so it's count. See, I always sometimes add an S there. Okay, so digits won't really matter here, right? But it won't matter here as well. When you have integers, I believe it spits out the entire integer. But if you have anything that has a decimal place, it'll give you the full number of digits for that number. So that'll reduce some of the complexity. I think it's better as a visual cue because I don't like to look at too many numbers. And it's relatively safe in the sense that it's not going to, I still trust Mosaic to actually do what I want it to do. And I can just sort of see what happens. Proportion, I like to add S's a lot, don't I? It's a little bit easier to read, but I really wouldn't round it. So that takes us to our rounding function. And I'm going to give you a really good example that I think is from class of, it's going to be a little bit of a soapbox, but a little bit of a case of why this is important because it comes directly from class. This was actually a student who came to me who said, did I get the wrong answer? Because she had actually looked at the analyses from one of the slides and had wondered, how did I come up with this number? Well, no, you were not wrong. Ethan Fosse, Dr. Fosse was wrong. How can the professor be wrong? Well, because there's a time for everything under heaven, as they say, right? You could be wrong for a particular reason, but when we're looking at, and I don't want to say we really value precision that much, because in statistics we don't always value precision, but we do want to make sure that what we come up with makes sense. And whenever we round, I want to think of rounding as something akin to any other function, to say a square root of something. It's a mathematical expression. Well, if you look at the equations that we present to estimate our outcomes, like I don't know, a standard error, that math does not include, say, squaring a term here or there, or adding a round to some decimal places that you desire here or there. And those get obscured into the recesses of the equation. And sometimes nobody knows what happened. And this happened, and I'm going to show you this example from a very simple case. It was the week on proportions, where we're looking at the 95% confidence interval on proportions. And I'll go to that. Unless I already have it open. Do I have it open? Do you guys have any questions, by the way? I'm gonna actually cut and paste the Wall Street data example. Okay. So when you look at percentages, yeah, this isn't scientific. No, this isn't scientific notation. No, I'm sorry. Whatever I said. This is, I would say the digits option is a brute force mechanism of defining the number of both integers and digits, at least when you do proportions, but I think not when you do other counts. So when you do the counts, if we force a number of digits to 1, I don't think it'll actually even be able to evaluate that, right? It won't. But when you do it to say something like %, oh, it doesn't even do it there. That's interesting. All right, so there's a little bit of mystery going on here. I think what's going on is when you have 1, when you specify digits to 1, it'll give you as much information plus probably that 1 decimal place that hangs over. And then when it gives you 3, it'll count those 2 whole numbers, or the actual numbers, the tenths place and the first, the second place here. 5, it'll give you the 5, it'll give you the 7, and it'll give you the 3. And if you ask for 1, it'll just give you the 1 digit, which suggests that if we ask for 4, we should actually see 2 decimal places. And that's exactly what we see. So maybe that explains what I thought was wonky before with the proportions. When you ask for 1 proportion, this is what it'll at least give you 2. Why would it give you 2 if you're asking for 1? Because of the first rule of probability. It adds up to 1. So that's actually kind of a nice feature, actually. I'll take my frustrations back. I rescind them. Because what the digits option is doing, argument you should say, is that it is not going to remove or destroy the logic of the digits that it does print. So whenever you have counts that are whole numbers, it won't give you fewer than that, because you can't print fewer than that, because it's a printing function. Think of this as cosmetics. It's not math. So if you want to do anything, go ahead and do the cosmetics, but don't do the math with the rounding function. Mea culpa, I apologize if I had encouraged that using the rounding function. But I do think the rounding function has a place, because it lets you control and actually decide when you are the one who knocks. In other words, when are you the one who decides when to actually impose your will on the data? And the cosmetics, it cannot do that, right? Because we cannot have a probability space a probability space is defined by 0 and 1. Ergo, all of these proportions are going to be bound by that. And what's interesting here is it'll include a 0. It's called a leading 0, if you haven't heard of that term. That's in typography too as well. I actually don't like leading zeros. It's a very common thing to exclude those whenever you have anything bound by 0 and 1. Because it doesn't make sense to have a 0 or 1 there if the highest you can, or have a 0 there, because it doesn't tell us anything. So if you ever read any psychology articles, anything that is bound by 0 and 1, like a correlation, will never have a 0. Because that set of numbers from 0 to 1 is defined by anything to the right of the decimal place. Just a little fun fact here, and I think that's what it's evaluating here. Okay, so I think we feel a little bit better about digits. And that's what you see here too. You'll see that these count to 7. I did count that. So when you do proportions, it's actually really not even counting that 0. So why do we even have that? Some people like to have zeros. When you do percentages, it looks like it includes the integer there. So, you know what? I would actually even say, and you'll see this with the output. Oh, and I want to say this actually does kind of round. So if you look at this, you'll see 57 here. Let's round this to 2 decimal places. So what are we going to do? We're going to define I think we'll define our digits to 2. Let's try that. We might have to do 4. No. 2, it'll actually round to whole numbers. But look at it. It successfully rounded it. And guess what? It did not destroy that information because we can retrieve it right back. And I'm going to actually prove to you that the options digits function. Options digits does not destroy. I use the word destroy information a lot, mostly because there's a statistician out there who does a lot of cool stuff. That's his phrase. He deserves credit. But I think it's a good way to think about it because data are expensive to collect, typically. Less, though. So let's define number 1 as, does anyone know pi very well? I don't know, 3.1456, blah, blah, blah. So I had a professor who tried to impress everybody by counting pi to 1,000 digits. And then everyone thought he was correct because guess what? He's a Harvard professor. He seems to know his stuff. And then he said, no, I don't know what this is. Because there is a limit to precision. It doesn't make sense to have overly precise numbers at some factor, especially when we're dealing with statistics. It's really all about ranges. It's about approximations. That's what we're doing. That's what a point estimate and a standard error defined together. It's an approximation. That's what an inference is. It's a best guess. So philosophically, I'm not that keen on precision. So I'm a little loath to or sheepish about saying you got to have the correct exact answer. So you don't have to be precise, but you have to be replicable. You have to know where you got it. And part of that's writing code, but part of it's also just doing the math correctly. So here we have this number. And we can define, I don't know what I did with options. Options digits equals 1. We should get a 3. So we're going to print this number 1. What are we going to see? We should see. Oh, I didn't evaluate this. So we did that, and then we should see a number 1. Okay. Well, let's do number. Oh, by the way, you can define objects plus 1. So we'll do add, and this is the assignment operator again. And then we'll do, by the way, I didn't have to do any of this because RStudio is very convenient here. It's giving us our digits here, right? I set this to 4 decimal places. It's telling us my addition, I added 1 to what I thought could have been 3 because I printed it out. Is 3? Nope. It wasn't a 3. It was 3 point. It was the object number 1 defined with all of its precise glory plus the integer 1. So that's enough proof, I think, for now. I could probably go more than many people care to on these kinds of things, but let's go to this issue of mid-rounding. I'm going to give you a little quote here. This is from another introductory stats book. This is a little bit of a soapbox. I'm going to read this to you if you can't read it. I should give you the source, but I don't have it. Let's see if I do have it, actually. No, I don't. I apologize. The concepts as well as the symbols used to represent them will be explained in detail in this chapter. This is chapter 1 of another intro of stats book. And I've heard it called before the general rounding rule. And that's what we saw in problem set 9. And some people came to me in class. In statistics, the basic rounding rule is that when computations are done in the calculation, rounding should not be done until the final answer is calculated. When rounding is done in the intermediate steps, it tends to increase the difference between that answer and the exact one. Now, this is what is important. But in the textbook and solutions manual, it is not practical to show long decimals in the intermediate calculations. Hence, the values in the examples are carried out in this book to enough decimal places, usually 3 or 4, to obtain the same answer that a calculator would give after rounding on the last step. Not exactly. It actually doesn't, and I'm going to argue against that last point because I've seen it happen. And in class, we really tried to give you partial credit at the very least, or even full credit, if we could divine that your answer was simply a consequence of rounding error. But that requires reverse engineering and tracing things back. And sometimes the propagation of error can be quite extreme through different kinds of logic. And I'm going to take this example from our week on proportions. So here's an example of an illustration. Well, what's the problem here? We divine our standard error and we round that to 4 decimal places. And a student of mine, in my section at least, then tried to come up with a z-score, and I believe rounded it, and I think came up with something slightly different. Because I think it was because she didn't round. So this is an example of midpoint rounding. There's implicit there, and this is for illustration. But it actually came up with this came up with a very slightly different answer. But I'm going to show you something else that came up with an answer that was like 16. Her answer was like 18.73, and she didn't know what was going on. And again, I think when it's a couple decimal places off, I don't think it's a big deal. So this is from week 11. And this is how we should think about decimal places. It's also an example of how to solve a mathematical problem of that logic here. Now, yeah, I said test statistic, z-test statistics found by observant students. So this is what she found. So I usually like to break things down. I like to work backwards when I think about math problems. Here you'll see me sort of use the dotted programming definition to define an object. Is everyone clear about what this little thing is, this assignment operator? It defines things. So everything to the right of that is what you want to define. So if I want to say, happy is, oh shoot, I didn't want to do that. Oh, I just restarted R. Okay, sorry. Did I lose everything now? No. Look what I just did there, by the way. By the way, here's the other tip of the century. If you don't like to type this out, a lot of people. So, well, I'll just define this first. What it's called the assignment operator. If you type that, you're saying happy is defined as the state of many smiles, or whatever definition you want. So think of it in that way if you want to think about it even in terms of language. And then you can see it printed out here. So here I basically define my word. Right? I can say Nate is stat E100 fanatic. In the good sense. Right? And then this is what Nate is, and we can print it here. I just do Control Enter. We have that. And this is important too, because I didn't really describe this, but you can define these as new numbers now. So A equals is assigned to 1, 3, let's say. B is assigned to the square. We're going to add a full function here, square root of 4. And then we want to do something. We want to do something a little complex. We do A plus B. And then we're going to evaluate that. Oh, you know what? We didn't define them. That's the problem. Then we got 5. Still doesn't tell us what B was, but we can see it up in our workspace. B is 2, because this is the square root of 4. Okay, so the point is you can use the assignment operator to define anything to the right as to the left. A lot of people who are into scripting languages can, and if they want to, they can use the equal sign. Google doesn't recommend it, but a lot of the newer people are, because you're using it in Python. So we can do A equals 3. Here's the reason I don't like it. Can you guess why I wouldn't like to use that? By the way, when you redefine functions with the same, so redefine global objects with the same set of characters, it will override those. You will not see it here because they're the same numbers. But I just overrode those. I rewrote those. So that's a little kind of an issue that I kind of don't like. A lot of programmers don't like this. But the point here is we have the same number. It's technically a vector that we can also define, right? So if I want to say answer 1 on my problem set is this. Again, I'm weird about these phantom parentheses. I just like to have them. I was never that good with mathematical order of operations, so this makes me feel a little more comfortable. And then you can do answer 1, and then boom, we got our answer. Beautiful. Oh, and if you want to know what proof that answer 1 actually is a vector, I think you can do another command called structure. It's similar to class. Oh, it's a numeric. It doesn't say it's a vector, but it's numeric. You can tell it's numeric, and it has a 1 value there. What is that? Answer 1. Where do you see that? We'll do the class of answer 1. Okay, so I think it's a numeric. I think it is a numeric vector though. If I add 1 string to that, if I add 1 word to that, and it's multiple, if I have 1, 2, 3, 4, 5 Nathan in the last element, those little bits of elements in the vector, then it's no longer a numeric vector. It's automatically defined as a string because when you put 1 string in, it messes up the rest. Yeah, the point is you can use equal signs. Again, I don't like to use them because equal signs are used often in objects, right? Or arguments. So it's a little confusing. And equal signs are also have this kind of property in math. What is the communicative property? Or maybe it's just the identity property, right? So it means that if A equals B, then B equals A. Well, what happens when we do that? Okay, so we got A equaling B. It doesn't say that though. Oh, because we define B as something. Look at that. See, this is the other problem about macro environments. So I'm going to do A equals X. This is one of the, you know what? I'm going to remove this. You can remove objects too. Just type them in. That's the easiest way for now. Separate them by a comma. And then you just remove those objects. There are other ways to do it too, but we don't have time for that. But removing stuff from your workflow is great. And you should do that on the regular, as I would say. So yeah, removes up. Especially if you're doing a lot of mathematical functions, you could propagate error actually. You could do more harm than good if you do that. I would just recommend, honestly, clearing your global workspace like this, commenting out the script, and then working on the next problem. That's how I do it. Okay, Control-Alt-C I use to comment out that. And so I want to show you A equals B, B equals A. Well, object A and object B don't. Oh, because we have to put these in quotes because these are strings. Okay, so we could define it. Okay, we're okay, I guess. But it still doesn't, it doesn't make sense because you could define B equal a number, for example. It's still R evaluates from left to right. Just always keep that in mind. It's not like Hebrew. It's not right to left, except in some weird instances. I was going to do that with this assignment operator. Okay, so why I don't like the single equal sign, the single equal sign. Someone likes to think of the equal sign as an if. B if the square root of 4. So semantically, maybe this is another scripting language, the assignment operator and equals, this is just another way to learn it, equal sign can be read as if. Not if and only if, just more of a colloquial if. Just it's always useful, I think, also to translate into sentences. Answer 1, if you add A plus B. Okay, cool. And you know, when I told you that you can, it reads left to right, most of the time it doesn't matter. But with that minus sign is a little tricky, I think. I don't think we want any more of that. Seems like the cool people in Silicon Valley that I know, I don't know that many cool people, I guess, but they seem to like the equal sign. Okay. A little hack. A lot of these people who hate typing out the assignment operator have to press one part of the key and the other. We know that programmers by definition are lazy. I've heard that all the time. It's a virtue. Laziness can be a virtue because it means efficiency. That's why I'm telling you to do this, because it's efficient. Don't do it the hard way. You know, if you're climbing up the hills, or if you're going to Machu Picchu, don't travel without the burro. Have the burro carry your stuff with you. Have the robots work for you. Okay, on a PC, I can do foo, which is kind of, I don't know, programming jargon for whatever it is you want to insert in your land. And I'm going to do it with the assignment operator. I can just hit Alt, and then that's the dash. And it includes the assignment operator and the space. So if you ever hear a programmer say, I like the equal sign, say, nope. Equal sign is a way to define arguments. It's also semantically confusing, and that's an important distinction to keep. And Google does it. And there's also an easier way to type things out. So I do foo equals 4. Did I type that too hard? Okay. Carriage return. Foo. I'll do underscore 2. Alt equals. That's pretty neat. Did you see where the cursor was? It was right at the end of that object, and it puts it all the way to the end. That's nice. 5. Carriage return. Okay, foo. Now here's another thing that the RStudio does. Okay, I want foo here. I'll press tab because that's what I want. And I'm going to press plus. And I should really type my spaces here. And I'm going to do foo 2. I press down, and then I press the tab to complete. So this is another way to save time. If you have long variables or long objects to type out, you don't want to type out Wall Street. For instance, if I type out wall, if I do, I don't know, names, it gives you a bunch of functions, but we don't want that. We'll do Wall Street. How many letters do I have to type? I'm going to type just the letter tab. Boom, control, return. That's my fingers feel nice already. Okay, so I gave you a hack on how to type the assignment. The rabbit hole goes deep, my friends. I was going to show you can actually type the assignment operator in the opposite direction. I was surprised because a very, 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 very quotable person in the R world, I heard them in Coffee Talk. You can do that? Yeah. You're surprised every day with what the world can bring you. Okay. Now let's take us back to class. I didn't want to. I think that was useful. I hope. Okay. All right. Good night, guys. Bye. Okay. Thank you. Sorry I missed the messages. But was I a bit late on that? Okay. You just left. Okay. No problem. Elizabeth, you cannot hear me. Okay.
No, I cannot.
Elizabeth, can you unmute yourself, perhaps? Let's see. I can see you. You're good. Hey, how are you?
Wait, hang on. How do I do this? Oh my God, I have no idea.
See, I can mute your audio, and then I can unmute your audio.
Yeah, I think you just did.
I don't know. Jason, do you have any intuition? I'm not sure. Okay. At least you'll hear the recording later. Okay. All right. Oh, I see why some people are leaving. It's a lot later. Okay, I shouldn't run into time for doing other things. Okay, let's go back to this mid-rounding conundrum. Okay, so this is from slide 43, I believe, if we cut and paste. Yeah. Example, the Y rounding issue. And again, I just want to emphasize, it's not the end all and be all, but you're going to increase the odds of confusing the graders, because if you get a slightly different answer, I might be able to guess, and it's common. But if you're the only one committing that issue, and you have a very logical, idiosyncratic method,
oh my god!
I won't.
I didn't do it. Yeah.
Okay. You guys are still hanging on with me? I know this is long. So.
Oh no, I didn't do this.
Shoot. Oh, okay, I'll open the script here. Okay, yeah. So this is sort of, this goes back to week 11, slide 43. So do we have the script of this scrupulous students? Yes, we do. So if we go to this slide, here's also an example of how to run the math here. So I like to break things out into their sequences. So maybe you want to define different objects here. So, and always use the full information. So we don't want to, if we don't want a mid-round, we really want this thing to be honking as precise as possible, right? So we can still define our standard error. We can still define our Z statistic. So let me see if I can split screen this a little bit. I'm gonna squish out my pane here. Yeah, it looks like I even did some intermediate steps here. I wouldn't do that again here. I think for clarity, well, it looks like this is what Ethan had done in the slide. He did the standard error and defined it with the equation. So we could actually do this. We could actually, it's actually easier to do this. Let's see what he did here. Where's the square root here? Oh, it's above everything. Why did I miss that? So yeah, we could do, well, what's the square root? What is it, this? You could do, oh, I see, that's SE squared. So I meant to define this first object as a standard error squared. I'm going to use the lowercase, the underscore notation. That is better. Oops. We all live and learn. Yeah, we got a lot of little parentheses here. We got more than we probably need. Remember, the order of operations is typically PEMDAS. This takes me back to middle school. PEMDAS, right? Parentheses, exponents, multiplication. I'll type out the asterisk. Division, add, subtract. Okay, sure, you can trust the world of PEMDAS. I typically like to just, I like to evaluate everything individually and precisely. So PEMDAS really would say, yeah, you're going to be able to do the multiplication and then the division, so you really don't have to do this. Right? This should you're pretty much okay, Mr. Math Wizard. And if we looked at the environment, we would see that be the case, I'm sure. So there's a SE squared. And look how precise that is. Look at that. Look at those digits. We're not getting that at all. And then we can do our actual standard error as we can redefine it, right? Equals, and we're going to use our square root function, and we're going to operate it on that object we just defined. And, well, that's way too long. Well, remember, we got our nice little digits operator here. So I'm going to remove these objects. We're going to start again. And remember, there's a comma between each of these. Press Control Enter, and you got those objects gone. I hate all this junk here. There's a way of removing all objects except for one. I don't like it. This is what I don't like about global objects. They just move around like people at a party, you know. They're nice people. They're useful. They're friendly. But sometimes you're tired and you want to go to sleep. These guys sometimes just want to go. I also want to show you with objects. Here's a good way to handle objects. Whoa! I didn't want to do that. That was a view. You should do here a tiny tab. You can actually view this as a grid. This is how you can, in GUI land, you can actually get rid of your objects. Just highlight those ones you want to get rid of. I didn't mean to be so dismissive about parties. That only happened once in my life, I think. Usually I was probably the one up. Okay, so remember you go to grid view, and you can just keep the data set that you want. Keep in mind for the final, you're not going to have a data set, but we're just keeping it here. Okay, so I just taught you how to remove objects. So, okay, we're going to redefine these things. By the way, you can still remove non-existent objects. It doesn't kill anything. It just complains. Okay, good luck, sucker. You're not going to remove anything. Yeah, we can do this. Again, I like to put spaces here. Why? To errors is human. Let's avoid that. Yeah, and I kind of like this because I just like to remember what it is I'm doing. I like to define my, I don't know, I'm just idiosyncratic that way. You can do your own thing. And I could talk about piping, but I'm not, We'll do it this way. I would say break it into the steps. Why not? Just do it, okay? We have this. Technically, we could just do this. In an ideal world, we could do square root of this. Can you see maybe why I don't like to do this, by the way? You know, some of the less programming stat packages are just awful. So what do you do when you have these many parentheses? Well, first of all, you can see that R is helpful. And if you have a Mac, it'll actually, if I press a carriage return, it'll match up my square root function right to the tip of that. It only gives me 2 spaces. Google likes to avoid tabs. I'm not really sure why, but they like 2 spaces between everything. But the point is, you can take these paired spaces, these paired brackets. I still like to line them up just so they look a little purty. You know where they're going. And then you kind of know, you can at least break down your arguments. You know, it's like parsing a sentence. Okay, cool. Okay. Who's there? Is Jason? Are you still there? That's okay. If anyone has to leave, that's fine. Elizabeth, if you have any questions, feel free to interject, all right?
I don't have any questions.
Now you can see the idiocracy of
I don't know if you can hear me.
Why is that there? Oh, I see. Okay. So one parenthesis defines the ratio. This defines that function. I think that looks a little silly. Well, what's going on? I'm defining the standard error as alt hyphen. There we go. And it's all this junk inside. Not a lot of junk, but okay. So here we have our standard error. So we more mimic the slide here, and we can see that it's small. Do we even print the standard error on the slide? Why is my standard error different? Oh, you know why? I forgot to square root it. There we go. All right, so you want to square root something. So now you can sort of see probably advantages of defining parsing complex operations into different objects. There are other ways called piping. I think I talked about it weeks ago, but I don't want to introduce too much new material. Okay, so let's go back to our options, and we're going to do digits equals. See how many Ethan had here. 4, maybe 5. Let's do 4 and see what we're up against. And then we're going to do SE, and that's just our convenience function for printing it. 1, 2, 3, 4, 5. So making it 5 there. So, oh, you know what? I think it's because it's not identifying zeros as digits. Right? That's not information. It's really just where you slide that decimal place over, which would make sense for the proportions. Sorry, I don't know more about the digits option. It's just sort of, it's not something that is really, as a data scientist, you're not doing this much calculation really, but it's instrumental for actually really figuring out and really getting used to R if you're not so inclined. All right, so that makes sense. So it defines the number of digits other than the null, the ciphers that sort of tell you where to stick the decimal place, right? You think of those zeros, I think of them as where to put the decimal place. Okay, so this observant student, what did she come up with? She emailed me and said, did I do something wrong? She blamed herself, and we'll see what she did. I replicated what she had done, and I'm going to simplify her work. Okay, so I'm going to go back to the default digits of 7, because this is what you're going to be used to seeing. She did this. Actually, I'm going to remove all the objects by typing this top one. This is grid view. I'm going to deselect Wall Street, and I'll remove everything except. And she came up with a z-score, and the z-score, of course, is the difference between the null and the the null, the alternative, and minus the null. Order matters. Order matters. This was a big issue, by the way, when you evaluated point estimates for differences in proportions, differences in means. The output shows that the order matters. We want to see the negative sign. And why? Because that's the math. But it's also the logic of thinking. It mirrors the hypotheses. You could have said 6 of one. You could have said half a dozen of one and 6 of the other, but you decided to start with 6 of one and half a dozen of the other. So there's this principle of parallelism, of logical consistency in the way they think. I'm going to use this rounding function for the very first time today, but here I define an object that is a difference. I'm not even going to do that now. I think we've done enough with our operators. Well, PEMDAS. Can we subtract before we divide? Not really. S is the last thing. So that's also probably why I kind of like to put my, maybe I do have a good reason to put my parentheses behind closed doors. Defining a whole ratio that is encompassed within a square root function doesn't really make much sense unless I get an error message. Like you. Typically, you get an error message. There's an unmatched. It says unexpected token. Okay. Still unexpected token. There we go. There's an unmatched parenthesis. But if you notice, R is pretty helpful, right? It can tell me which is paired with what. Okay. That's another, by the way, you don't have that in calculators. Okay. So we're going to take, what is this? Okay, we take our difference and we divide it by the standard error. Well, look at this. We got our difference and we're going to divide it by our standard error. And we got it to full main line precision here. What? Did I do a remove function here? I actually just want to evaluate this one. Okay, we got it now. Right, that's pretty hefty. overkill. We evaluate our answer. 18.78 blah, blah, blah. What? The instructor got it wrong. The student said, did I do something wrong? I said, no. He rounded because the eye can't handle the truth. You know, that's gobbledygook. My eyes are already glazing over. So this is an example of propagation of error where, yeah, I know the source, but I can't divine it after ex post facto. Okay, so that's the one thing. So then I just basically, and then, so if you want the right answer, you can do the digits option. So how many digits do we want? Well, if we look, we can look at our environment. We got our Z. We're going to tell you to round it to 2 decimal places. So we want 4 digits here, right? We don't want our 2. We want our 10. We want our 8, and then we want our 2 decimal places, and it will round us for you, and it'll never destroy that information in that object, which is kind of cool. Sorry, 4. Let's see if that works. And then we got to print. I like the little form. No, I won't be formal. There we go. That's the right answer. That's beautiful. And you want it again? You want it again? I'll give it to you as many times as you want. I'll give you everything. And then if you think I'm wrong, professor, I got it. I'll show it to you. That's another reason. You know, you have an audit trail. I had a student send in our code as part of the assignments. That's actually very intelligent. I mean, it's increasingly, you're seeing a merging between science, production, and the back end. And there's actually a lot of LaTeX code. I know some of you are interested in LaTeX. You can actually embed the code within. Pretty cool. Right? I don't like to, I actually like spaces. I don't know. The Kansan and me, wide open spaces. Okay, so there we came up with an answer. Now we can also do the, what I would call the Z underscore round. I'll do that. And we'll do the assignment operator, Alt. And the, this comments, I don't like this. I actually don't like these kind of comments that are tacked on. It violates this idea that your syntax, your script, you've got 80 characters. Because, you know, some people will just write the syntax on and on. You have to do the scroll bar, and then you're losing. It mucks everything up. Try to stay within the playing field. Okay, so what does the rounding function do? Only one kind of rounding. Keep that in mind. So I'm 100% certain. I believe it rounds anything that's, if it's at 1.5, it will round up.
Yeah, so now we have to leave, right?
If it's at a 1.49.
We have to leave, right?
Yeah, we're shutting it down.
Yes, integer if you're rounding to the nearest integer.
I'll grab your glasses.
There are other kinds of rounding. Don't do that. You can do a floor, ceiling round. I think there are other kinds of rounding, but do this. So we're going to take our our output to the digits, 7 digits, and then we're going to comment this out. This is the messiness that we've been showing you all semester that you're not going to see. Ah! Let's round it myself. Okay, I'm nervous. Mistakes will happen. Mistakes have been made. There are researchers who actually identify the number of mistakes that people make, especially in psychology. They use a lot of user-friendly software. And your cognitive biases, you cannot escape them, especially with p-values. Apparently, people tend to round toward just significant p-values, or they'll tend to round. So if it's a 0.51, they'll tend to round down to 0.5. And I don't think they even notice it. I think it just kind of, we like to see what we want to see. So that's happened to me, by the way, a lot of times. Not when I'm actually working, but I'll think something is like totally awesome. I remember this once. And I thought I found something really cool. And then I just, I don't know, I took a 5-minute walk and I came back and I realized that was just tilting at windmills, thinking I was finding something. Okay, the round function. This is the old the old way you see in practice set 9, you can print that, and there you get the same answer. Yeah, okay, great. That's kind of cool, but let's look at our environment here. Ignore this. This is the last object I evaluated. Here we have Z, and we have ZR. ZR, we've just killed information. Okay, not a big deal. No big, you're saying. All right, I will try to help you and grade it correctly. Errors will propagate. If you are going to get hired as a data scientist with your data science certificate, you want to avoid that mid-rounding, because it's going to piss people off. You were going to work in a team, and someone's going to ask, how did this happen? I'm not going to say planes are going to fall out of the sky, because I don't think a lot of engineers use R really. But it's hard to audit your trail. You know, it's like Hansel and Gretel, and then everyone else eats up those crumbs. It's nice in theory, but it doesn't always work. Still, I think I kind of like it, because you are at least being explicit about what you're defining. So if you really want to just grind down those data, or you want to just pound out that value, and you're getting a little worried about what these digits mean, because I'm probably not as consistent as I should be. This is as clear as the day. This is what you would do on your graphing calculator. It's most analogous. So hold on. Where's the video?